All right, welcome to your briefing. We're going to be talking about the invisible forces that are going to shape every single flight you ever take. Now, this isn't just some textbook meteorology lesson. No, this is about understanding the massive rivers of air that can either save you a ton of time and fuel or turn a routine flight into a real battle. So, let's learn how to read the wind.
I want you to think of the atmosphere as this huge invisible river system. As a pilot, you absolutely have to know how to navigate its currents. It can be a powerful tailwind pushing you along, saving time, saving fuel, or it can be a turbulent headwind that costs you both. In the next few minutes, you're going to learn how to read this river on a global scale.
So, first things first, we have to understand the fundamental power source that drives everything in our atmosphere. You just can't navigate a system until you know what makes it tick.
It really all starts with the sun. It's pretty simple, actually. The equator gets absolutely blasted with direct, intense heat, while the poles, well, they just get these weaker, glancing rays. This simple temperature difference, that's the engine. It drives every major wind system on the planet. It's the ultimate source of the power you're going to be working with or fighting against.
So this uneven heating creates a huge energy imbalance. And nature, well, it always tries to balance the scales. You get hot, light air at the equator rising up, creating a low-pressure zone. Meanwhile, up at the poles, cold, dense air sinks down, creating high pressure. And what does air always do? It flows from high to low pressure. That's simple flow. That's what we call wind.
Now, if the Earth didn't spin, wind would just flow in a nice straight line from the poles to the equator. Super simple. But it does spin, and that adds a really crucial twist to everything.
And that twist is called the Coriolis effect. Think of it as the steering wheel for our whole atmospheric engine. Because the Earth is spinning, any object moving over its surface, like a mass of air or, your aircraft, it gets deflected. You have to know which way it's going to turn because it dictates the path of every single major weather system out there. And here are the rules of the road. It's actually pretty straightforward. In the northern hemisphere, where most of your flights are probably going to be, the deflection is always to the right of your direction of motion. In the southern hemisphere, it's to the left. This is a non-negotiable law of physics, and it shapes every weather pattern you will ever encounter.
So what happens when you combine that big solar engine with the planet's spin? You might expect chaos, but you don't get chaos. You actually get a surprisingly orderly system of what I like to call highways in the sky. It's all organized into what we call the three-cell model, and this is the blueprint for all global air circulation.
Take a good look. This right here is your foundational map of the atmosphere. Notice those three distinct circulation cells in each hemisphere. You've got the Hadley cell down near the equator, the polar cell way up top, and then the Ferrel cell stuck right in between. This three-cell structure, it's the key to understanding all the prevailing winds you're going to encounter.
So let's look at how these cells work together. The Hadley cell is the real powerhouse, driven by all that intense heat at the equator. The polar cell is its cold counterpart, driven by that sinking polar air. And the Ferrel cell, it's kind of like the connecting gear between them. Together, these three form a massive conveyor belt system, constantly moving heat from the equator up towards the poles.
And this is really where it all comes together. The interaction of these cells and the Coriolis effect creates the world's major wind patterns. For example, those westerlies, they are exactly why your eastbound transatlantic flights are almost always faster than your westbound ones. Understanding these winds is absolutely fundamental to efficient flight planning.
Okay, now for the part that's going to directly impact your flight time and your fuel consumption. We're moving up in the atmosphere now, to where you'll spend most of your time, and where we find the real expressways in the sky.
So, how do you actually use this knowledge in the cockpit? Simple. You use it to find the jet stream. This is a high-altitude river of wind, just screaming along at 100, sometimes 200 knots. If you can catch a ride on it, man, you can shave hours off your flight time. But if you have to fight against it, well, it can be a long, costly, and pretty bumpy ride.
Now, jet streams don't just pop up randomly. They form right at the boundary between cold and warm air masses. So when you're planning your flight, you're going to be looking for these sharp temperature gradients on your weather charts. That's the spot. That's where you'll find these high-speed winds.
There are two main ones you're going to deal with. The polar jet is the stronger one, and it sits at higher latitudes. It's driven by that big temperature difference between polar and mid-latitude air. Then you have the subtropical jet, which is a bit weaker and sits closer to the tropics. Knowing the difference between them and where they usually are is going to be critical for your flight planning.
But these high-altitude rivers of air don't just affect your plane. Oh no, they're deeply connected to the weather we all experience. Their position and their strength literally shape the weather for everyone down on the ground.
Okay, let's connect this to some real-world weather you've heard about. On the left, you've got El Niño. That's a warming of the Pacific Ocean that can literally push the jet stream way off its normal course, which causes droughts in some places and floods in others. Then on the right, the monsoon. That's a seasonal wind shift that brings predictable, heavy rains to places like India. These aren't just random events, they're driven by the same large-scale patterns we've been talking about.
So it's really important to understand the difference between general circulation and large-scale circulation. That three-cell model we talked about, that's general circulation. It's the idealized textbook theory. It's the why. But the real world is messy. Large-scale circulation is what you actually see on a weather map, the real dynamic systems like El Niño and monsoons. You need to know the theory, but you fly in the real world.
Ultimately, this knowledge is so much more than just meteorology. It's about developing a new sense, an ability to see the invisible architecture of the wind. Understanding these patterns is what will make you a safer, more efficient, and more intuitive pilot. Briefing complete.